Okay, now we talk about line integrals of vector fields. Okay, nice application. So one of the applications that we want to do in science is if we have a particle in either a plane or in space, and there is a velocity, there's a field acting on the particle, like a velocity field or gravitational field, something of that nature. We'd like to know, but let's think it's more interesting, right? It's a velocity field, like wind, something like that. Wind acts on the particle and moves the particle. Well, I want to be careful. The particle, let's say, goes from one point to another point in space. All the while it's doing this, there is a velocity field, or let's just say a vector field acting on the particle. It could be electric field, velocity field, whatever. We'd like to know what work the field does in moving the particle from one point to another point. Okay, we'd like to know the work, and the work could be positive, it could be negative, it could be zero. It depends on the path that the particle takes, and it also depends on what the field is. So the scenario here is what you see here in figure 11. In figure 11, you have a particle that goes from an initial point p sub 0 and goes to a point p sub n. So what we'd have to do, of course, is the vector field, the vectors in the field, act upon every point on, well, the path that the particle makes. Every point on the path, the vector field is acting on that point, okay, at some time, right? And if we were able to compute the work, all the little pieces of work at each point on that path that the vector field does in moving the particle along that path, then we could add up those work values and compute the total work. So you can see in the picture there at the point P sub I, that xi, yi, zi point, there is a vector field that's acting on the particle. And a component of that vector field F actually contributes towards moving the particle along its path. And that would be in the direction of the tangent vector. So if we have, if you think about the definition of work with two vectors, what is the work? What operation do we do on the two vectors to find work? Do you remember? What operation? In multivariable calculus, we define work as the what between two vectors. Well, Juliana, not the cross product, but you're almost there. It would be the dot product. That's right, Ellie. Okay, Juliana agrees. Okay, very good, very good. So we could take the dot product in this figure 11 at that, looking at that point P sub I. We could take the dot product of the vector F at that point, and the tangent vector, the unit tangent vector T, okay, and compute work. But of course, if we want the work that the force field does in moving the particle at that moment on the path, it would be, of course, I want to say this the right way. I want to say this the right way. Well, of course, the arc from the point PI to the next point could be represented by delta S. Okay, and so you see the distance that the particle moves would be, or I want to say this the right way, the tangent vector, that unit tangent vector, is, we don't want to use that because the particle isn't going to move a whole unit, right? It's going to move just, it's going to move in the direction of the tangent vector by some scalar. Well, the natural scalar to use would be delta S, a little piece of arc length. That would be the natural scalar to use. So then, what we're doing then is we're saying that the work done by the vector force F in moving the particle from one point to another point is approximately equal to this dot product between the force field vector and a scalar multiple of that unit tangent vector. And it would make sense that the scalar multiple be delta S, which is that little piece of arc length. And this is going to be then that little piece of work. And the total work then that the force field does in moving the particle along that path would be the sum of all the pieces of work. Okay, that would be it. Now, obviously, as we sample more points along the path, this summation here, going from I equals 1 to n, if n were let to go to infinity, and we sampled a lot of points on the path, what would the limit of this summation be as n goes to infinity? What would the limit be? What would it turn into? What would the summation turn into in the limit as n goes to infinity? Well, Riemann sum as n goes to infinity, that's right, Ellie, it's going to turn into the integral, right? So, and that's going to be your work. So then the work that the force field does in moving the particle along that path from one point to another is equal to this line integral with respect to arc length over the curve C. That's going to be the work. So hence, it's good you know about line integrals, right? It's good you know. But then all the properties you learn with line integrals apply to this kind of situation. Now, the tangent vector, you know, what variable do we want to get involved in here for this problem, for computing the work? We don't want, and you know, I'll mention that the particle, when the particle moves along this path, remember, okay, in figure 12, each point is the particle, as it moves along the path, it's doing it with respect to time. So the tangent vector is that t vector, that unit tangent vector, is a function of some time corresponding to when the particle is at the point x, y, z. Okay, so the tangent vector, well, the tangent vector is a unit vector, right? And what we can do is, if we, you know, here's the work. So if we were to rewrite the tangent vector, we could do it this way. Tangent vector, you know, is the derivative of the position vector divided by the length of the position vector. And the ds can be replaced by the length of r prime of t dt. Okay, that would be how ds dt would be. Let me just see one thing here. Let me just see one thing here on this. Yes. So there then is an expression to find the work. Okay, and we call that the line integral of the vector field F along curve C. And if we go down here, I mean, there again is the formal definition. And we denote that in shorthand notation by the integral of F dot dr. Okay, now why would that be? Let's go ahead here. Let me go to the whiteboard. One moment. Okay, let me go to the whiteboard. So the work is equal to the integral of your vector field evaluated at the points, but the points are given now by the position vector r prime of t dot, no, the points are given by the position vector r of t, right? And then that's dotted with the vector r prime of t dt. Now, we'll note here that r prime of t is just dr dt, right? dr dt is r prime of t. So that means r prime of t dt is equal to dr. So this is why r prime of t dt is just dr, and we can denote this just by f. I mean, we know f is a function. We know the vector field is going to be the value. The vector is going to be a function of the position that you're in the field. So hence, shorthand notation is, oh yeah, and it's over some path C. Shorthand notation for work is equal to this. Okay. Just trying to keep it nice and simple for us. Nice and simple. Are there any questions on that? Okay, well then this then makes sense then, the definition. Okay, so I'm very careful when I explain things. I am very careful because I like to think simply when I look at things like this, and I think it helps you too if you can look at things in a simple way. There's always a why, usually, you know, why things are true, and if the more whys we know, the better off we are, right? So let's go ahead here and get to an example. Well, we've looked at a lot of examples, but I got one here that we can use here formally in your notes. So let me give you a moment to copy this down, okay? And while you're doing that, let's see, Arian, can you hear me okay? Maybe give me a thumbs up if you can hear me all right. It's nice to have you with us here. All right. Kino, how are you doing? You doing all right? Okay, I hope people are here. Gordon, how are you doing? Good. Emma, how are you doing? You doing all right? Feeling comfortable with the material? Good, good. All right. Okay. All right, let me give you a moment to copy. Thank you, Hunu. Yes, I really, I try to call everybody at one point or another, but thank you, Hunu. Um, all right. So in this problem, we're trying to compute the work done by a force field in moving a particle along a quarter circle that starts at 1, 0 and ends at 0, 1. Now, what would be nice to have would be a picture of this situation. Okay, so in Blackboard, you have a program here. I'll show it to you that I wrote actually specifically for this problem. Okay, so if we go into the Blackboard here and go under MATLAB programs, there is a section 13.2 line integral program that will show you how to graph a vector field over a space curve, and it relates to this problem here. So let me bring that one up. Okay, let me bring that one up. Give me one moment here. Okay, and you bring it up too. Okay. Now, one thing I didn't put at the beginning of these programs is the clear variable statement. Okay, but you can always in the command line, right? You can always in the command line, hold on. You can always type clear variables. Okay, so what we have here is we create a mesh grid. We're going to create a grid of values. And this grid of values, you notice that the x goes from 0 to 1 with a scale of 0.1, and y goes from 0 to 1 with a scale of 0.1. And the reason that makes sense is we're restricting ourselves to the first quadrant, the quarter circle in the first quadrant. So why would I want to have anything else? Let me have a graph. Let me have a window that makes sense. Okay, so the component, the I component is x squared, the y component is x times y, and again, I'm using the pointwise notation, okay, so that MATLAB won't think that I'm multiplying matrices. You know, what happens is MATLAB stores when you create the mesh grid, it stores all those points in a matrix. And I don't want MATLAB to think that I want to multiply the matrix. I want to do pointwise operations on all the values in the matrix. So I'm going to use the quiver command. You've seen that before. Quiver command will graph the vectors, right? And then I'll have a graph of my vector field, but then I'm going to say, hold on, because I want to now graph my space curve using the linspace command. And x and y are cosine and sine. So, all right, let's take a look here at what this, let's go ahead and take the code, copy it, and paste it in here. And let's see. Okay, and let me find my graph. Okay, so I guess I have to stop sharing this. Wait. Okay. So who's getting a figure like this? Who's getting a figure that looks like this? Okay, excellent, excellent. Ian is. And there's the space curve, and we're overlaying the space curve. The particles moving from the coordinate 1, 0 to 0, 1, and we superimpose the vector field, the force field given by components x squared, comma, negative xy. So let me ask you, when we compute the work, do you think the work that the force field does in moving the particle from 1, 0 to 0, 1, you think the work would be positive or negative based on the force field? Is the force field helping the particle move along that quarter circle path from 1, 0 to 0, 1, or is the force field overall acting against that movement? Juliana says no, that the force field's not helping. It's actually impeding the movement. Okay, so the net work, the overall net work, we should get a negative answer. Okay, so this is helpful, right? This is helpful. Maybe on the exam next week you have a problem like this, and you can get an idea of whether the work should be positive or negative. And incidentally, we don't have I mean, if you were to do something with a force field in three-dimensional space, and a curve in three-dimensional space, you could adapt this program to that, right? Just, it's not hard to figure out how to do that. Okay, well, that being said, let's go ahead and go back to our example. Okay, and so let's now find this work. Let's find what it is. So, all right, the vector field is x squared I minus xyj. My parameterization of this space curve for the quarter circle is cosine of t I plus sine tj. And this picture here and the comments above, it's this figure 12 is from example 7 in your book. That's what we're doing here. I'm just applying now the definition of the work, and I get a dot product. Good, Kino. I'm glad you're back with us here. Excellent, excellent. And of course, the t limits go from 0 to pi over 2, because it's just the path here. If I highlight the path, I'll highlight it in red. Say I did that pretty well. Well, now, so this is the direction, right? You have to I mean, one thing that's always good to have is the direction of the particle, right? At t equals 0, the particle starts at 1, 0. And at t equals pi over 2, the particle ends at 0, 1. So that's why you have your limits. Okay, and when you work it out, you get down to here. Please let me know if you have any questions. Now we have an integral to do, right? We have an integral here. And gee, how are we going to do that? What integration technique are we going to use to do this integral? And by the way, you know, this is, of course, we're doing the dot product here, right? This is the dot product here. What integration technique do we use? What do you think? Integration by parts, substitution, partial fractions. Well, you know, I'm not saying integration by parts won't work, Ian, but a substitution might work here. What might we let u equal to? What might make sense? Let's see if a substitution works first. So remember what this is here. This is the integral from 0 to pi over 2. I'll bring the negative 2 out front. I have a cosine squared of t, but that's like cosine of t squared times the sine of t dt. What substitution is going to work? That's right, Ellie. Very good. The cosine of t. That's going to work here. That's going to work. So on the next page, here we go. I let u equal the cosine of t, then du dt is negative sine t, so du is negative sine t dt, so negative du is sine of t dt. And the limits now get changed, right? You have an integral with respect to t. It's got to become an integral with respect to u. So this top limit here is pi over 2, right? So how do we get 0? Well, the cosine of 0 equals, I'm sorry, let me do this again. So the top limit here is pi over 2, right? So how do we get 0 here? That's just by taking the cosine of pi over 2. And then we have a 0 on the bottom. How do we get a limit of 1 here? That's the cosine of 0. That gets you 1. So our u limits go from 1 to 0. A lot of times students are uncomfortable having the bottom limit larger than the top limit. So if we absorb this negative here, if we absorb the negative, okay, we get then, instead of an integral from 1 to 0, wait, hold on. Wait. Oh, no, I didn't absorb the negative. I didn't do that. I brought the negative out. We have a negative here and a negative here. That makes a positive 2. And look, let's just work with the limits as they are. Put them in, and we get negative 2/3. So our work is equal to negative 2/3. And it makes sense that the work's negative because the force field impedes the movement of the particle. It impedes the movement of the particle. Please let me know if you have any questions. Okay. All right. Well, then let us proceed on. Let us proceed on. So now, if there are no questions, we'll look at another example. Maybe give me a thumbs up if you're good, if you're comfortable with this. Okay, thank you, everybody. Okay. All right, let's look at something else. So this integral here, the integral of f dot dr over a curve C, what's that stand for again? That stands for, when we compute that integral, we're finding, as you recall, the work. Well, it turns out the work really can be thought of as the sum of two line integrals. Okay, what's this notation mean here? This is the sum of the line integral with respect to x over the curve C plus the line integral. Well, I want to be careful here. So this notation here, this notation stands for the sum of two line integrals. The first line integral is the line integral of where your function is p, and you know, p is a function of x and y, of course, and q is also a function of x and y. They don't state that there, but we know that they suppress the x and the y, but they are. P and q are functions of x and y. So this work is actually equal then to the sum of two line integrals. The first line integral would be the line integral with respect to x over the curve C where your function is p, and the second line integral is the line integral with respect to y over the curve C where your function is q. Okay, so when you're doing homework problems and you're computing line integrals, particularly when you're computing the sum of two line integrals, what you're really doing is finding the actual work that a force field does in moving a particle along some path based on a vector field, where the vector field has I component P and J component Q. Okay, so let's go ahead and see why this is true. So first of all, what I do is, okay, well, work, of course, is equal to this integral here, the integral of f dot dr over curve C. And what I do is well, what is that vector field F? Vector field F, of course, if we're integrating with respect to t, the vector field F, well, the vector field F is computed based on the a point that you're on in the vector field. Well, the point that you're on in the vector field, the XYZ point, is equal to some position vector r for some time t, right? So that makes sense. And then dr is just r prime of t dt. Okay. Well, now what I'm going to do is I'm going to write out my vector field F. Okay. So my vector field F this is a two-dimensional vector field, and the vector field F has components P, okay, which is a function of x and y are functions of time, and it has, so that's the I component. The J component is the Q function, which is a function of x and y, and that's functions of time. And then R prime of t is just x prime of ti plus y prime of tj. And we're doing the dot product of those two vectors, right? The dot product. And when we do that, we're going to get this integral here. P times x prime of t plus q times y prime of t. Okay. But, of course, then, we can write this single integral. Okay, we can write that as the integral of a sum is the sum of the integrals. But x prime of t dt is just equal to dx by virtue of the fact that dx dt is x prime of t. So dx equals x prime of t dt, and y prime of t is just equal to dy by virtue of the fact that dy dt equals y prime of t, hence dy is equal to y prime of t dt. And so you end up getting then the sum of the two line integrals, one with respect to x, one with respect to y, and hence the final result, which is a notational result. Okay, are there any questions on that? Okay, who's comfortable with that proof, making the connection between the work and then some of the line integrals? Does this proof make sense? Is it okay? Maybe give me a thumbs up if you're good. All right, Kino's good. Okay, and Ellie and Charles and Juliana and Malik, and then some other folks too. Never can see the last two. I don't know why. I have to figure that out, but one thing at a time. Excellent. All right, I'll stop the recording here.